Thanks for coming and for letting me speak. So let me recap quickly what we saw last time. We considered this kind of eternal black hole in this hybrid system of JT gravity and two flat space regions. And we computed the entropy of the bath, which is like the Hawking radiation, as a function of time when we evolve the two boundary times forward in this way. And we found the following thing. We found that the entropy of the bath simply increases as a function of time linearly, modulo what happens at early times. And this was in conflict with the behavior of the coarse-grained entropy of this black hole, where because of the static nature of this space-time, the coarse-grained entropy is simply a constant, and it's equal to twice the usual Bekenstein-Hawking entropy at a given mass, simply because you have two horizons on the two sides. And so here, this exhibits an information loss paradox, namely because the fine-grained entropy of the radiation exceeds the Bekenstein-Hawking entropy. Therefore, it seems like the black hole can have more entanglement with the radiation than it has room for. Okay.
You could also have done this in higher dimensions, right? In fact, you could literally the same calculation to go through.
Literally.
So this is just computing the entanglement entropy of the slices outside.
Yes,
The
yes.
fact that these slices stretch out.
Yeah.
Just one more comment. The paradox, in a sense, as you said, pointed out in EDS, the paradox doesn't arise because the entanglement entropy is controlled by the size of the regions outside, which, as you said, you may not be able to stretch too much.
Oh.
In EDS, you were saying because of the reflecting boundary.
Exactly.
I think that's effectively a reflection of the fact that the regions outside don't get too long.
Exactly. In some sense, that's correct, yes.
Right. You could phrase the paradox even without going into entanglement entropy just by estimating the size of the Hilbert space.
I agree.
Which you could do here. So, you could just count the number of pure states, all of which have entanglement entropy 0.
Yeah.
But, because the volume of the slices becomes so large inside.
That's right. But that everything said is correct. Although here it's just, I like this version better just because we know how to get to that state from a case where there's no problem. Right? The state at t equals 0 is a very sensible state, and we don't have any paradoxes and so on. And we naturally evolve into a state which seems to have the paradox. But everything, as we said, was correct. Okay? And so why is this problematic? The first issue is it seems to, so these are, I'm just reviewing the standard set of words that people say when they review the information paradox. This seems to say that you can have objects in quantum gravity that can have an arbitrary number of states below any given fixed mass, right? These are usually called remnants, right? So one resolution of the information paradox is that when the black hole evaporates away almost completely, all the Hawking radiation is actually purified by some very, very small mass object, but which must have an arbitrary number of states at that given small mass. And this is problematic because, one can say that it's in some sense ruled out, essentially by sort of particle physics experiments, in that if such states do exist, they would pollute scattering amplitudes, they would run in loops, because everything couples to gravity, and if you have an arbitrary number of these guys, no matter how small the gravitational coupling is, they would contribute to any scattering amplitude and mess up the results that we see at the LHC. Okay, so that's one argument. The other argument, which I like better, is that this observation is simply not consistent with ADS-CFD. Okay? One can imagine here replacing the bulk, or replacing this picture with this picture, where we replace the bulk spacetime with the dual boundary theories. These left and right systems, you can think of them as two SYKs, for example. And in this case, a large von Neumann entropy of LR would mean that there's a large von Neumann entropy of LR. Sorry, I don't know if I said that correctly. So the large von Neumann entropy of the bath, BL and BR, would imply a large von Neumann entropy of LR for some given again, for some given coarse-grained entropy of LR. But so for holographic theories, we expect them to have to always have a finite density of states below any given energy. Here, the energy of LR is fixed, but it seems like if we evolve to the future, like this, the entanglement entropy between the union of BL and BR with LR would grow arbitrarily large. That would imply that this holographic system, LR, has an infinite number of states at some given fixed energy. That's problematic. So ADS-CFT tells you that this result must be wrong somehow. Any question about these arguments? Okay. Okay, let me give you maybe a simpler case.
So are you saying that the density of states is
always finite? Correct.
It's not continuous.
Correct. That's what we have in ADS-CFT.
But if I look at the Title-1 theory, if I look at the density of states function, then it is not.
Correct. That's right. So you might worry that this model is somehow sick, and it allows for this feature. But I will argue against that later. Okay? But let me give you a more general argument, because somebody wanted me to review this. Say you have ADS-CFT in higher dimensions. We know that the vacuum is unique. We just have the ground state of the CFT. Imagine we have an evaporating black hole inside the system where, so we have a black hole that transformed into Hawking radiation, and we somehow extract all this Hawking radiation outside of this ADS system. All this Hawking radiation, by assumption, by this calculation, is mixed. So it should somehow be still entangled with the CFT, which has no energy in it, so it's very close to the vacuum. And we know there's only a few number of states near the vacuum. So there's not enough states in the ADS or in the CFT to be entangled with all of this radiation that you extracted, whose entropy can go as 1/g Newton. Did that make sense? Question?
You could have done the same thing, of course, in Riddler space by drawing these slices this way, right? By starting at any spatial infinity, drawing the slices, the Riddler horizon, and then you get, I think, the same answer for the. It would not be a paradox there because the Minkowski space does have an infinite accuracy. What's happening is the slices inside between the two Riddler horizons are probably becoming very. And in this situation, the paradox is that you do have a finite density of states. Finite geometry just can't support these long slides.
Here I have finite. There I don't. Thank you.
So, finite geometry requires the Hilbert space to grow arbitrarily large, which shouldn't be.
Exactly. And so the expected answer. So somehow this puzzle needs to be resolved, and the expected answer for what the entropy should look like is that it should somehow follow the initial growth of the entropy at early times, but then transition to the coarse-grained entropy. So the entropy would grow as fast as it can, given the temperature of the system, how fast it's evaporating. But then at some point, it maxes out how much an entanglement it can have, and then it would just follow the coarse-grained entropy. It'll just be a constant. Okay? This curve is called the Page curve. Okay? At some point here, this time when this thing transitions, this is often called the Page time. Okay? So the whatever resolution you have for the information paradox should kick in at the Page time. Okay? Now let me say that if somehow we manage to reproduce the Page curve, I claim that this is tantamount. Oh, sorry. If you reproduce the Page curve for both systems, so you take the two baths, and you compute the entropy, and you find that it follows the Page curve, and you also take the LR system and you also compute the entropy, and you also get the page curve. You need to do those two separate calculations, and you need to check that SLR is equal to SBLBR, and that they both follow the page curve. So you should not assume this, is the statement that I'm making. And I would say that if one was to reproduce these results, this would be tantamount to resolving the information paradox, at least as sort of phrased by Hawking, right? The issue that Hawking found, I mean, he just computed the entropy of the radiation, and he found that the entropy just keeps growing. So if you just so just at that level, the problem that he points out, the entropy keeps growing, so you just need to fix that. But this does not, so if we get this doesn't mean that we understand everything about the quantum mechanics of black holes. I think this is a really important point. For example, something that you need to do is show that there's a one-to-one map, for example, between initial states and final states of the radiation. Right? That's a much more fine-grained calculation. I will resolve the first part. I will not give you the second part in these lectures.
Sorry, now you're making a statement about the full theory of quantum gravity.
Well, yeah, so the full theory of quantum gravity should reproduce the page curve and all these other features that I discussed as well.
We have this issue of how you define the quantum.
Yeah, exactly. And that's going to be the thing that I'm going to build up to. But for this lecture, I'm still in the phase of reviewing all these issues about evaporating black holes, but again, in the context of this guy. The next question I want to address, if there are no questions about what I just said, is to realize these ideas of Hayden and Preskill, which is a statement that if I throw a message into the black hole, just a message M, this black hole sort of continuously exchanges Hawking radiation with the bath. Do I expect at some point that this message will appear in the Hawking radiation? So we know that if the black hole is actually evaporating away, then anything you throw in should appear in the Hawking radiation. But in this setup, when it's in thermal equilibrium with the radiation, do I expect the message to come out? That's the first question. And the second question, if so, how fast does it come out? Okay, that's a question of Hayden and Preskill. And I claim those ideas actually apply in this case. You do expect that the message will come out of this black hole, even though it's in thermal equilibrium. To do this, I will consider a very simple qubit model, just where I'll set things up to mimic this thermal equilibrium situation. And I'll show how, in a cartoon way, how the information will come out. Let me see. I'm going to, sort of in the back of my mind and in these pictures, I'm going to assume this picture. So where the radiation is the union of BLBR and the black hole is the union of LNR. So before I go to this picture, let me draw what the Hawking radiation does as a function, how it gets exchanged between the black hole and the radiation. So there are two processes. The first process is where Hawking radiation sort of entangled across the horizon, how one member of the Hawking pair escapes the black hole and makes it into the bath. Okay, so that's the first process. The second process is where you have a pair of Hawking modes so these guys are entangled. Everything is, in this space-time, it's all symmetric. A mode here is always entangled with a mode there, and so on and so forth. So those two guys are entangled, but at this time, at t equals 0, they're both contained in the bath. But as a function of time, if I evolve them, one member will fall into the black hole. but the other guy stays in the bath. Okay? So in this case, one of them stayed in the black hole and the other one escaped the black hole. Here, one of them stays in the bath and the other one falls in. Okay, I'm going to represent these in terms of this entire space-time in terms of that quantum circuit. For now, ignore this M. So these are actually 7 qubits. They compose the left-right system, and actually, maybe I should erase. Let me see. No, it's fine. Okay, so here we have 7 qubits, which are on the left-right system, and here we have the bath. There's some entanglement between the black hole and the radiation. I should say that I'm focusing on this region, okay, where we're past the page time. That's supposed to be represented, even though it's not clear here, represented by maximal entanglement between the black hole and the radiation. The reason why, so maximum entanglement usually means that all the qubits are entangled, but I'm including this because I'm going to send a message in. But you should ignore this for a second. So what happens here is a function of time. Again, this is a toy model. There's a step of some sort of internal scrambling of the qubits of the black hole, and a step where there's an exchange of qubits between the black.
Qubit are
these lines. Yes. So there's an exchange of qubits between the black hole and the radiation. So this blue line here, it represents a qubit that escapes the black hole and makes it into the radiation. Okay, that's like this thing right here. Okay? The orange line is, I have 2 entangled pairs. One of them goes into the black hole and one of them stays in the radiation. That's like this process. Okay? So one of them falls into the black hole and one stays in the radiation. Okay? So that's this picture. And then I'm going to model the evolution in I'm going to repeat this. There's some scrambling, and then there's an exchange, scrambling and an exchange, and so on and so forth.
By scrambling, you mean some unitary operation?
Some unitary operation acting on the Hilbert space of LR.
Just say one more, I know you're saying things in relating to all them, you're creating different should resolve, but there's an assumption which is that the bulk corresponds to LR and the bath is separate.
Yeah.
Which is not going to be true later, right? Because the bath is going to invade the bulk. So the
That's right.
I mean, I don't want to put this, but I just want to point out that if you,
No, but this picture is true irrespective of what your interpretation is.
Yes, it's true for LR coupled to BLN.
Exactly.
It's not true for the bulk coupled to the.
Yeah.
If you take the bulk picture, then it's not clear how much.
Ignore this.
Yes.
So.
It's true for the right.
No. So the picture is this.
Yes. For that, I agree it's true, and but the right-hand side picture is not equal to the left-hand side.
This is the picture that I need.
Yes, and for that will work because that's an ordinary quantum field theory which doesn't have declassification.
Yeah.
But for the left-hand side, it's just never been clear to me whether you really expect in what sense you should make it.
Sure. I agree. If you agree with this picture, which is really the same thing, it's the important thing for the process that I'm considering. Here we have some thermal equilibrium between LR and BLBR, and that's represented by this quantum circuit. Okay, so now let's include a message qubits, these 3 qubits, and we want to show or understand how the information about these message qubits end up in the bath system. Okay. One thing I'm going to need to show this is the concept of a random tensor. So random tensor has the following properties. First, so let's consider a tensor here with 4 legs. This thing can be thought of as generating a maximally entangled state of 4 qubits. Okay? So when drawn in this way. One can also put arrows on these qubits. So I can put sort of an arrow this way, down, down, up, up. This thing can now be thought of as a tensor that looks like this. Okay, so 2 in, 2 out, and I drew them in this way. Then this tensor becomes a unitary transformation between these two to these two. Okay? The punchline is that these random tensors are unitary transformations, to good approximation, from any half of the qubit to any other half. Okay? So that's the thing that I'm going to use to show how the message M appears or propagates to the bath or the radiation. Okay, so let's put arrows as sort of information of M going in. So it goes like this. Now I'm going to cleverly choose how to direct the information in these tensors to get what I want. The first thing I'm going to do is I'm going to, so these 3 guys are going in. Now, so I need to choose 7 legs. So I should have said, this is 7 to 7. I should choose 7 legs to go out. But I have to choose which 7 in a smart way. I'm going to choose these bottom 4 here. Okay? So these now says some of the information goes this way. Okay? So these 4 already, they went to the bath. And I need to choose 3 guys up here. I'm going to choose this blue one and 2 more. Okay? Okay, so now let me propagate these guys forwards. I didn't put any arrows here. I'm going to put them in later. So here, it's a statement that even if I don't push information here, let's say I fix the state of this guy, then this is going to be an isometry from 1 to 2, right? So I have these 3 that go out. One of them goes into the bath, and I have 2 qubits going into this unitary. So 2 are going in. I need to choose 5 to come out. Sorry, I need to choose 7 to come out still. There will be 5 coming in. So I need to choose 7. So let me choose the orange guy. So it goes like this. And let me choose the blue guy. That's 2. Let me see. Just double check that I have this right. Okay. So now I have 5 to go. I'll choose these guys coming back here to be going out. Okay. So this means they just flow downwards like this. And I have 1 more to go, which is this guy. Pushing this qubit up. Now I need to choose 7 to come out from this qubit. I'll choose 1 down here, 1 up here, and now I have 5 to go, and here they are. 1, 2, 3, 4, 5. So now let's see how the information goes. So where it goes on each tensor. On this tensor, we have these 3 going in, and these 4 coming in, and we have these 4 going to the bath, and these 3 going up, or one of them going to the bath, and these 2 going up. Now on this tensor, we have these 2 guys coming in, these 4 guys, and these 5 guys coming in, and we have these 4 going out to the past in some sense, and the blue qubit going to the bath, and 1 qubit going here to there, and over here we see that essentially these guys can be thought of as coming in. The information about this now has been directed to the bath or the radiation, and with 5 guys coming backwards. So we see that all the arrows that started here really end up in the radiation. Okay.
What is the state of the black hole?
The initial state of the black.
What is the state of the black hole?
Yeah. Let's ignore M for now, for a second. So ignoring M means I ignore these 3 lines, and these 3 lines, and these 3 lines, and these 3 lines. The initial state is a maximally entangled state with the bath. Then we throw something in, and we see how, so we throw something in, and in this process, we have this exchange of qubits between the black hole and the bath. And in some sense, what this is saying is that the black hole is getting more and more entangled with the bath. So that everything in the black hole is entangled with something in the bath, including the message that you've thrown in some sense. And that's why that's the thing that allows us to conduct this pushing procedure from here to there. Okay. Any other questions? Okay.
Sorry, I don't quite understand how you make the distinction between these lines and one stage. So you had 4 lines coming out of the unitary.
This one?
Right. And from the blue lines that are coming out here.
In some sense, these are composed of blue lines in the past. I'm saying, let me start at late times, at the page time, where the black hole starts maximally entangled with the radiation, irrespective of how we got to that stage. And that's represented by these 4 qubits entangled in this way. In terms of how unitary.
You start with the system, the maximum entangled, you add some other thing which is initially disentangled. It also gets entangled with the other. How can you get any more entangled because you enlarge the workspace now.
So when we threw M, LR is not maximally entangled anymore because of these guys.
Right picture that the bath consists of things to get entangled with.
Yes, exactly.
Keep going in and keep entangling more and more.
Exactly. Precisely. So this is often, this setup is often phrased in the following way. What we do is we say, let's consider a system N, so let's call these 3 qubits M. We have a system N that's maximally entangled with M. So you maximally entangle your message with a reference system. The point of that is, in some sense, to study the system where you allow all possible messages. Okay, so that's one way to think about it. And the question of whether the information about M is contained in the black hole or not is the question of whether the density matrix of N LR factorizes. Okay. If this happens, this tells you that there's no mutual information between N and LR, which essentially says that N is maximally entangled with the bath or with the radiation, right? Because we started N was maximally entangled with M. But if after some time N becomes maximally entangled with the bath, that means that M is now in the bath. Those are the usual words. And in terms of, one can show that if you choose these unitaries to be Haar random, then you find the following result. That if you integrate, if you measure sort of the distance, the distance between this guy and this guy in the trace norm, for example, you find that on average, if you average over these unitaries in the Haar ensemble, you find that this is roughly, bounded from above, but very close to it, the size of the message, M, times the size of LR divided by the size of the bath. So this is D. And by the size of the bath, I mean sort of the subsystem of the bath that is involved in this process. Obviously, the bath is infinite dimensional, but I'm just considering just the set of qubits that are participating. You can write this, the dimension of the bath is simply the dimension of LR times the dimension of the extra radiation qubits, these orange and blue qubits that were involved in the process, and therefore this thing is just equal to the dimension of M divided by the dimension of these new radiation qubits. So what this tells you is that if the amount of radiation that you so this is dimensions. We can write this in terms of the number of qubits, right? This goes as 2 to the number of message qubits minus the number of radiation qubits. So we see that if you collect if you go through sort of the number of steps of this process or collect an amount of radiation qubits, which is, say, 5 more qubits than the message, then this is true to the accuracy of 2 to the minus 5, which is pretty good. So you don't need to collect too many qubits of the radiation, just a few more qubits larger than the size of the message that you throw in. Okay. So one punchline here is that there is indeed a Hayden-Preskill protocol for this black hole. Now the question is, how long does one need to wait for the message to come out? So here's where sort of some physics comes in. Yes? Can you raise your voice? Yeah, the dimension is like the, sort of more physically, it's like the, I guess, coarse-grained entropy or something. Yeah. That's right. Yeah, so the question is, how long do we need to wait for the information to come out? Here's where some physical input needs to come in. So obviously, at any given time here, if you allow me sort of infinite power, I can instantaneously act with a Haar random unitary. Okay? And this will give me this result. But this unitary is supposed to be the Hamiltonian of LR, or e to the IHT of LR. And one expects that this Hamiltonian involves, is in some sense local. For example, in the SYK, you have n qubits, but the Hamiltonian acts on 4 fermions at a time. And so, translated to this picture, it says that you should think of you as composed of simple gates. By simple gates, I mean they act on, let's say, 2 qubits at a time. And now the question is, how long do you need to take to make this unitary random enough to give you this answer? This is the same U, by the way. If we require that this unitary be Haar random, then when composed of simple gates, it takes an exponential amount of time and the number of qubits for the unitary to actually be Haar random. But it turns out that Haar randomness is overkill. What we need actually, the minimum sort of condition is that we need something called a 2 design. These are unitaries that agree with the Haar ensemble up to the second moment in U. So they agree up to the U dagger, U dagger. This is what I mean by second moment in U. And here I mean I, J, K, L, M, N, O, P. Okay? So if it agrees with the Haar ensemble up to something like this, then that's called a 2 design. And it can disagree with the Haar ensemble for higher moments. And so this actually turns out to be a very simple kind of circuit. And one can show that these circuits can have logarithmic depth. The depth of these qubits goes as log of n, okay, the number of qubits. So that's like the series of steps going from this stage to this stage. So there's a log n number of steps there. And so the thing that Hayden and Preskill extract from this is that in the context of a black hole, there should be a scrambling time, some t scrambling, which is the thing required to scramble these qubits from at each step, which should go as log of the Bekenstein-Hawking entropy of the black hole. That's like that measures how many qubits you have in a sense, and then to make the dimensions correct, you put beta here. Okay, so the prediction is that after this time scale, the scrambling time, the information thrown into a black hole should appear in the Hawking radiation. Okay, so this is in some sense, a fine-grained probe of checking unitarity. So later, when I have more things to say about this black hole, we should somehow see that if you throw some information into the black hole, after a scrambling time, it should be reconstructible in some sense. It should be contained in the radiation. Okay, that's the thing that we want to. I will reproduce later. I will be able to reproduce it in the left diagram. I'll tell you, Subrat. I'll tell you.
I mean, is it claim that you expect something like this to work even for the left diagram?
With the right prescription.
If the right prescription is the right diagram, then that.
No. In the left, so there's magic involved, and the magic tells you can continue to work in the left diagram, but with the right prescription. Okay. Next up, very briefly, is the. I don't need this guy anymore. So this naturally leads us to the idea of black hole complementarity, right? This is weird. This thing is so the information paradox says the information is lost, but this result tells you the information is not lost, and then the observation of Lenny and friends with this black hole complementarity picture is that it seems that if you have unitarity, the black hole now clones information. Not only does it preserve it, it doubles it. So the idea now is, I made this worse. Okay, is that say I throw in a message into the black hole, somehow after a scrambling time, the message should be contained in some qubits, degrees of freedom in the bath. Okay? An observer, I guess in this case, two observers, one here and one here, should be able to sort of cooperate and be able to decode the message that was thrown into the black hole purely from degrees of freedom in the bath. Okay? That's what that picture is telling us. Information comes out, and so the information must be contained here and here. But then this is problematic, because these two people, they can collect this information. They can collect this information and then jump in and have in their lab 2 copies of the same quantum state, right? There was the message here that fell in and the thing that they decoded. So this is problematic, and what Lenny and friends wanted, or the way that they wanted to resolve this, was to use that result, the fact that information comes out after a scrambling time, and the idea is that if you have to wait a scrambling time before you get the message from the radiation, it's always going to be too late for you to jump in and actually observe the clone of the message that you extracted. Or you need to access some trans-Planckian physics and so on and so forth. Okay? So I'm not going to review that argument because I don't think it's actually essential. Yeah. So there is a cloning paradox. But actually, let me see. Maybe I went ahead of myself. Yeah. So what Lenny and friends want to say is that there's a way is at that time scale, they need to wait to resolve the cloning paradox. And they wanted to say that there is, in some sense, a kind of complementarity, which they call black hole complementarity. Let me tell you where the word comes from. So in quantum mechanics, you can measure the position of a particle or its momentum, but you cannot know both at the same time. If you measure one, you affect the other. And so that's what they wanted to say. They wanted to say that, in some sense, the constraints space-time somehow knows this principle, that you're not allowed to measure information outside and inside at the same time. You can only measure one or the other, and they have some sort of dynamical constraint using that time scale and blah, blah, blah. Okay. And so then they say, let's, quantum mechanics, you have postulates of quantum mechanics. So they wanted to define postulates for this black hole complementarity. The first postulate was, they're trying to come up with a set of rules that supposedly have no contradiction between them, and which are the following. The first is that you have unitary black hole evaporation. I'm going to call that just unitarity. The second postulate is that in the region outside the black hole, you have semi-classical physics. The physics can be well described by QFT on curved space, or QFT defined on sort of an adiabatically evolving space-time. I'm going to write that as semi-classical physics outside. The third postulate is that a black hole has a finite dimensional Hilbert space whose size or dimension goes as e to the Bekenstein-Hawking entropy of the given mass m. Okay, so these were the postulates, and apparently there's no paradox contained in them. I think they want to say that. They wanted to say that.
You can see this, you don't need a black hole. And one of the points that Mark raised, the fact that you have this kind of closing paradox should be there regardless of whether there's a black hole or not. You need the two evidence in such way you can set up a closing paradox of this kind. But you can resolve within what you know about ADC. The fact that those degrees of freedom are not independent from the degrees of freedom. In 1993, they did notice this. It's the fact that guy limited doesn't commute with that. You can derive it. This was a fortunate thing that they made it. You understand much more.
This leads us to the firewall paradox. So the point here is that there's an implicit assumption, or an implicit postulate made here, which is that an observer can actually jump inside the black hole, that there's a smooth horizon. That's something that we called postulate 4, which we called the no drama postulate. Meaning that you can jump into the black hole and the horizon is smooth, and you can actually, try to catch up to the message or do whatever experiment you want to do behind the black hole horizon. And the claim is that there's a contradiction now between these postulates. To see this, it's a very simple argument. To see this, let's again consider this region past the page time. And let's state the implications of each of these postulates. First of all, so we're not going to throw a message in. What we're going to do is analyze the state of the quantum fields in this space-time. Okay, so we're looking at some late time like this. We have two modes. Let me call them, should I do this wrong? Maybe up down here. Let me make it outside. Let's call this A, and this mode A tilde. Okay. Let me also define B as BL union BR. From postulate 1, so the fact that from postulate 1, unitarity, the fact that the entropy doesn't grow at late times tells you that SAB, when the Hawking mode A joins the bath, it can't increase the entropy. Okay? So SAB is less than or equal to SB. Right? So when A joins the radiation, the entropy does not go up. From the no drama postulate, P4, we have that the horizon is smooth. This means that we have the vacuum state at the horizon, which means that A and A tilde are entangled. They're in the thermal field double state, if you recall in the first lecture. So S A tilde is equal to 0, and that S A is greater than 0. So there's actually entanglement between A and A tilde. Yes? This is fine-grained entropy. I'm just computing the entropy of some quantum fields on some fixed background. This is von Neumann entropy of the various subsystems. Correct.
While you're setting up the paradox, could you add P5, which is not stated, which is space factorizers, which is the only situation? You just wouldn't be able to set up the time, right? So there is a P5, which is the inverse space factorizes black hole and radiation.
Yes, that is ultimately going to be the thing. So. Let me see. I don't know if I want to. Yeah, sure, okay. No, I like this. No. I want to do this. No. I really want to do it. I'm trying to recreate history and then. Please. Okay. I don't know. I had a lot of fun in 2012 when this happened, so I'm trying to make you guys really also live that. That's yeah. I guess I should have written sort of up here, no spoilers or something. Okay. Yeah, and then there's postulate 2, which is, I guess, just postulate 2 just says, I'm not going to write it down, it just says that the mode A can be thought of as just propagating on some fixed background. Nothing funny happens to it. Its state over here is the same as its state over there. That's what I mean. Okay, now the claim is that there's a contradiction, which comes from strong sub additivity of entropy, which is the following relation, that the entropy of A tilde B, so we're applying strong sub additivity to these three systems. This thing plus SA is less than or equal to SAB plus SA tilde. Let's apply the postulates to this thing. SAA tilde is 0 by postulate 4. And because AA tilde are in a pure state, this thing is just equal to SB. Okay? So both of these are by postulate 4. By postulate 1, we know that this guy is less than or equal to SB. And we're done. Now we have SB plus SA is less than or equal to SB. Subtract SB from both sides. We have that SA is less than or equal to 0 in conflict with this guy. Okay, so this is the firewall paradox. It's so simple, you must be surprised how this became a paper. Anyways, so we have a problem. One of these postulates has to give. Be quiet, Suvrat. It seemed to us that the most sort of the least undesirable conclusion is to say that postulate 4 is incorrect. So we want unitarity, we want semi-classical physics outside to be good for 2 reasons. One, we're sort of living on the outside and things look normal, but also in all attempts of trying to modify this, there are other paradoxes, and we want the black hole Hilbert space to be finite. So we give this up.
Small one. Sorry. Actually, repeat one before once again. What is no drama?
It just means that you have the. Let me write it again. So there's a state of the. So I mean that the state at the horizon is the vacuum. So in Minkowski space, for example, you have the Minkowski vacuum can be written as e to the minus beta e, or n omega, n Rindler, and left, right. So the Minkowski vacuum is an entangled state of Rindler particles. That's the same thing here. So the fact that you have the vacuum at the horizon is an entangled state of these of A and A tilde. That's what I mean by no drama. And so now we're breaking this. So this thing is no longer true. And so we have a firewall at the horizon, which from this argument, sort of, this setup only applied at the page time, right? That came from P1. So it seems like at the page time, something funny should happen. Blue is not a good color. So something funny should happen at the page time. There should be a firewall. So it's interesting. It seems like after some time scale, some new physics should come into the black hole, which was not there prior to the page time. I'm surprised nobody threw tomatoes at me, because this space-time is boost invariant. If there's a firewall here, there's a firewall everywhere on the horizon at all points. Everywhere here, and also you can do this experiment in the past, everywhere here, everywhere here, everywhere here. So it seems like this space-time is not really the eternal black hole or whatever, or these two, well, yeah, this space-time just doesn't exist. The wormhole, the eternal black hole is not a thing. We really have these two disconnected spacetimes. That's what the firewall paradox would say. Yes? Yeah.
It's about this P4. So suppose you think about it as follows, that you're working in Minkowski space, right? Suppose I make a Euclidean black hole space-time. Okay, then I Hawking and give a calculation of the entropy of the black hole. Now, there the geometry is perfectly smooth, everything is fine. So it is known. I mean, I'm talking of space-time being smooth, actually.
Yeah, but the.
Yeah, but
Sorry, there are two things. Okay.
not really rigorous, right?
But it's okay outside the horizon.
There is nothing like outside the horizon Euclidean space.
Correct, but then when you continue it, you'll get the outside the horizon.
Spenta, can I say two things? It's good. Okay. The first point, I was going to say what Suva said, but the second point is that this is actually a red herring. There are no firewalls. This argument is wrong. That's ultimately what we. Sorry.
Only the hand that erases can write it.
But it's going to fail because of a very interesting, I think, new observation in this context. Okay.
Last week, that the
page time is there's something new physics happening on page time, then just say
No, so the statement as you made it is not correct.
what is the
Good. The statement here is that if there's a firewall at this point, this spacetime has a boost symmetry. So I can just apply this boost symmetry, which is, like that, which pushes point on the horizon in this way, and so on. So if something was singular here, it must also be singular here. Yes. No, because
that's what classical GR would tell you.
no, I think really the entire state and the geometry and everything has a boost symmetry. So
I mean, you have some having Hawking radiation and so on.
yes.
So
Let me. Okay.
so you're ignoring that when you make a mistake.
No. Let me try to say it a bit differently. Let me see.
In a Hawking state, so that thing has boost symmetry. So there's no Hawking radiation coming out. Everything is time independent.
I mean, there is Hawking radiation coming out, but the state is boost symmetric.
There's the same amount of radiation going in, despite the boost symmetry.
That's right.
Boost symmetry is in a Hawking state.
That's right.
The same amount of radiation going in depends on the radiation going out.
No, going in and going out, that's just a potential of the fields outside. The flux of the stress tensor is, there's no finite flux of the stress tensor. So there's Hawking state, so they just
Said slightly differently. So we were evolving this guy forwards in time, something like this, right? And then we saw at this time there's a paradox, right? But I could have done things slightly differently. I could have, for example, kept this end fixed and just evolved this side. This would actually mean that I need to wait double the time, actually, all the way up there, and that's when the page time would be. So this was where it was before. The reason being is that I can boost this, bring this guy down here, and bring this guy, take that guy up there. So had I done the experiment in this way, the firewall would appear at a later time. But I could have done this even, I could have fixed this to some later time here.
I'm trying to understand is what are the things which are boost symmetric? Because everything is boost symmetric. Then there can be an evaporation.
Then there can be?
Then there can't be, like a page curve.
No, there can be. There can be, because the time evolution that we're considering breaks the boost symmetry. Right? We're evolving both times forwards in this way. Had I done this, then the entropy would be constant and there's no page curve and nothing. But I'm just saying I could have evolved. I could have evolved in a way that breaks the boost symmetry in many different ways, which would imply the page curve would come in at different times in some sense.
Why is that? So different evolutions have different firewalls. Is that possible?
Yeah, because that would say, in one evolution, I'll tell you the firewall is here. Other evolution will tell you that the firewall is there. Another evolution will tell you it's there, it's there. I mean, so if you scan over all possible evolutions, it'll tell you that the firewall is everywhere. I guess that's sort of what I'm. Sorry, I couldn't. Well, I'm trying to find out where is at what location is a firewall created, or when is it created? I'm saying because I don't want it to be an observer-dependent thing, you need to put the firewall everywhere.
Why can't the firewall be observed?
I mean, why can't it be observer-dependent? But I mean, the way that we phrased the problem, it didn't really care about the observer, right? I mean, let me see.
What's the problem now? The argument is that you have a quantitative geometry. So here there's some exact description. The firewall is not a statement of quantities, it's a statement of geometry. Yeah, so some geometry. So the statement is that in this exact description, there's an exact if you want to. If the firewall appeared somewhere, you have a problem because then the full space can not be. That's the argument. So the full boost symmetry, if you take it with there's no evaporation either. There's no, but that's true here. There's no real evaporation happening. The Hawking radiation is increasing because you're pushing slices up. Time dependence is evaporating to the path.
But the bath is also throwing in things. And
so the time dependence was happening because you're pushing the slices up. That tagging that came was not really because evaporation was happening. This is an eternal black hole. It never really evaporates. It's not really evaporating black hole. This is an eternal black hole. There's no firewall. That sounds like. But he's saying
no.
There is the paradox also appears for eternal black hole. I mean, not get to the firewalls, the firewall paradox for that. But the entropy of the black hole, the entropy of the radiation, Hawking radiation. Is it time transition?
No, it depends on which time you mean. So if you evolve boost time, then it's constant. But if you consider time that it goes up on both sides, for example, then it's not constant.
Okay. So the point is that, that's the same thing with the firewall. Okay. That figure there. Think of that as maybe a black hole slice. Now he has these slices which are going up on both sides. On those slices you compute the fundamental entropy, it looks like it's increasing. So it looks like there should be an infinite amount of enhancement. And that would have come about in the usual diagram, because if you look at the length of the slice in the middle, that length would have stretched. The firewall comes pointing back at it. No, now the firewall has appeared at some point when the boost appears. Firewall depends on the no. Just look at that diagram. At some point, maybe if you draw the line at that point, the entanglement fundamental entropy of the fields outside became larger than SPH. So how could that be? So since we don't have P5, we say there's a firewall. But now that firewall has appeared in the geometry. Now you have geometry. Just look at the blue line, right? So I understand that it should appear after page time, but in page time, in that funny time where you're pushing time up on both sides. So now, but now the whole geometry is boosted, so it should be everywhere. It can't appear on the horizon suddenly at that point. But that's a statement I don't understand. Now let's do a boost. So you shift the position of the points. So if you change the slices, you have a different firewall. This is a question, but the firewall is observed. Why can't you have like a horizon in these? Either the geometry has a large two-point function, or it has a small two-point function. Either it's well behaved or it's not well behaved. And the two-point function is a covariant thing, that's dependent slicing also. If it's badly behaved, you get some argument to say it's badly behaved. Which two-point function? There's a two-point function of quantum fields across the horizon.
This region.
And now, if you argue that that's badly behaved, then you're in trouble because now you do a boost, you will move that bad behavior somewhere else. Within all these assumptions, while you're making all these mistakes, then you should also make the mistake with the firewall.
Okay. Very good.
The flat space black hole, which does evaporate. The Schwarzschild black hole does evaporate.
Sorry, does or does not?
It does evaporate.
Okay.
Flat space Schwarzschild.
Formed from collapse, let's say.
Yeah.
Okay.
And then there is there any problem forming a firewall after base time?
No. Because there we don't have a boost symmetry. Okay. So this is the firewall paradox, and now we can let me state one resolution of this paradox, which is what goes by what Suvrat was saying that there's a P5. I'm not going to write down what it is, but that there could be, we're assuming that the Hilbert space on this entire slice factorizes. And the idea is that somehow, maybe, that the interior physics is somehow encoded in the exterior. This goes by many names, and a lot of people worked on this, including Suvrat. And the title that I want to give this is what Juan and Lenny proposed, which is ER equals EPR. Which is somehow, after the buildup of this entanglement, something funny happens. This picture of local factorization of the Hilbert space fails, and somehow A tilde, so this is A tilde, this is A tilde is somehow contained in B. And you can show that if you assume this, that this strong sub-additivity argument that I gave doesn't apply, and there's no paradox, and so on and so forth. I'll go over that very quickly. So the idea is that now there will be no paradox between this P1 and P4.
When was this paper?
13, I think.
Was it before these people's work or after?
I don't know. That time was just a blur. Everything came out at the same time and not the same time, and.
Yes, we have the internet as a time set,
Yeah.
etc. So nowadays you can't.
Yeah.
I mean, in the past we have suffered a lot without the internet. But today you cannot.
We can update the website or something. Okay. Yeah. Okay. So let's take an example. Let me say that B, somehow the Hilbert space of B is somehow composed of A tilde, tensor some B tilde, the complement of A tilde. Let me just apply these postulates and just show you that there's no paradox. So from S A tilde equals 0, we have that the density matrix of A tilde, B tilde, is equal to the fact that A tilde is pure. This must be something, this must factorize. So there's a pure density matrix, tensor rho B tilde. Okay? Tracing over A on both sides, this will give you rho A tilde B tilde equals rho A tilde tensor rho B tilde. Okay, that's simple enough. Now if you compute the entropy, so this thing is B, from this. Computing the entropy, this will tell you that the entropy of B is equal to the entropy of A tilde plus the entropy of B tilde, which means that SB is greater than or equal to SB tilde. Okay, so that's one result. The other, again, from this, if we simply compute the entropy, so again, this thing is B, this would tell you that SAB is equal to, from this guy, SA tilde plus SB tilde. This is 0 by postulate 4, so this is just SB tilde. And from this and this, we find that SAB is less than or equal to SB. We obtained postulate 1. Okay? This is just a very simple demonstration that once you assume this, everything works out.
The argument that you just written below
Oh, here, okay.
So the statement is that you just change the SP, the different term in the left hand side with SP theta. With that removes the paradox.
No, it's not. It doesn't make sense to write A tilde B, because A tilde is a subfactor of B.
But whatever if it is, it won't give you SP, but it will give you something like SP theta.
Something like that, but I want to emphasize that this argument was phrased assuming the Hilbert space factorized into A tilde, and B. So even the phrasing doesn't work when we assume this. So now there's no paradox. You can't formulate a paradox. But we can say things like this. You can draw many. Say that again.
Show that the Hilbert space is gravitation.
So far, I didn't show you anything. Yes. So what I was going to say is that in their paper, for example, the Susskind and Maldacena, they just considered some examples, but they didn't really prove it. Right? They just said, what if, essentially. And the next thing I'm going to talk about will be towards proving that. And so how much time do I have? 10 minutes.
Is it a good place to stop?
It is a good place to stop, but I might have a comment or two to make. So let me just see. I might finish, and if need be, we'll do one more. But 80% I might finish. 80% probability that I might finish. So I think maybe this is a good place to stop. Thank you.